Welcome everyone. Today we'll be looking at the notes worksheet entitled Right Triangle Trigonometry Day 4. And so what we'll do today is just take a look at some of the harder right triangle trig problems. And then what we're going to do on the back side of your notes worksheet is actually define the trig functions for the third and the last time finally here. So really as complete of a definition as possible for sine, cosine, tangent, cosecant, secant, and cotangent. So let's start it out here. I have three examples on the front side just to have this as the culminating piece to the right triangle trig that we've been looking at. So let's start it out. I'm going to read example 1 and we'll go from there. To measure the height of a mountain, a surveyor takes two sightings of the peak at a distance 900 meters apart on a direct line to the mountain. The first observation results in an angle of elevation of 47 degrees. The second observation results in an angle of elevation of 35 degrees. And then what is the height of the mountain? So I like this one. It's a good realistic approach to right triangle trig, and it's a little above and beyond what we've seen thus far. So obviously with my diagram and what you decide to draw, you can do this a couple different ways, but ultimately we're going to sort of get the height of a mountain taken care of, kind of like that piece. And then let's take a look at what's going on. It looks like a surveyor is going to be sort of on level ground, kind of like this, and is going to take two sightings. First is going to result in an angle of elevation of 47 degrees. So everyone, what you're going to do is just find a spot somewhere in here if you don't mind, and then let's go ahead and get that angle of elevation taken care of, which would be 47 degrees. Something like that. And then, just based on the way I'm reading this problem, it looks like the surveyor is going to go 900 meters back. And so from here to here, everybody, I believe we're going to want to have as our 900, and I'm hoping I'm reading that right as well, and come back here and now take an angle of elevation, or a reading, where that angle is going to be 35 degrees. So the 47 degrees obviously has to be the closer of the two. 35 degrees is definitely the farther of the two. And what we're going to be looking for here is really the height of the mountain. I'm going to go ahead and label this H for right now, and then we'll kind of work with it. But you can kind of see how this one's going to be a little harder here. So I would ask you to maybe even pause the video for a minute or two and kind of look at it and see what piques your interest. I will say that there's definitely going to be right triangle trig. I should note that there is a way to solve a problem like this using a combination of non-right triangle trig and right triangle trig. But because our background at this point is only right triangle trig, we're going to take that approach. Okay, so let's figure out how we're going to play this out here. The way I'm seeing this, and I'll try to draw this on the board as best as possible, is that we do have one right triangle, kind of this smaller one right here, and then we have a larger right triangle, kind of this larger one right out here. And so if I look at this smaller one right here with the 47 degrees really doesn't have any values for the sides. I have the H, and as a matter of fact, the way this is going to progress, everybody, is I'm going to call that X right in there. I have two variables. But I'm going to at least set up an equation here and kind of go with it, and I'm hoping you would all agree with me that it is the tangent of 47 degrees that is equal to that height over the adjacent side there, which I called X. So I have tangent of 47 equals H over X. Now, of course, one equation in two variables, it's no good. It doesn't allow us to solve for H. But two equations, two variables, allows us to maybe move forward with this. And so now, everyone, what I would ask you to do is look at the secondary right triangle, the big one, and let's see if we can write ourselves a nice equation using those same exact two variables. Let's see if we can play it out here. So I'm seeing it, everybody, as the tangent of 35 degrees. And now if you look at that big right triangle, everybody, the opposite side is definitely the H. And the adjacent side is really from here all the way here to the base of the mountain. And in this case, I'm hoping you would agree with me that it is 900 plus the X. So one equation, two variables, it's a no-go. Two equations and two variables, we can play with it. And so we're going to do exactly that piece now. Now what I'm going to do is kind of remedy a couple situations up on my board here, and you can follow suit on your paper if you can find a different approach, that's perfectly fine, of course, by me. But I'm going to go ahead and kind of bring that x on up. So I'm going to say x times the tangent of 47 degrees. That's equal to h. And then I'm also going to remedy this one over here. I'm going to bring this on up and say that the 900 plus x times the tangent of 35 degrees, as a matter of fact, that's also equal to h. And so you can kind of see, just by me cleaning out the denominators in those two fractions, that I've basically created two equations where they're both equal to the same variable. And so I'm hoping you can kind of take the next step forward with me in that this is equal to h, this is equal to h, so what do we know? Well, they're definitely equal to each other. And so I'm hoping you now see we went from two equations and two variables, now everybody, to one equation and one variable. And that is something I can deal with. Now, the numbers are not going to be pretty here, but I think we can play it out as best as possible. So I like this one. It required two different right triangles in order to set this up, both in two variables. And now what we're going to do is break this on down and solve for one variable at a time. So what you would do is grab your calculator at this point. I have some numbers on my paper here that will hopefully get us in the right direction. But basically, we should see that the tangent of 47 degrees is just over 1. And if we know our values of tangent, that should make sense. And then what I would do is take the tangent of 35 degrees, that's right here, and distribute it into the 900 and distribute it into the x. And so when I do that, everybody, I get this. And again, you can play this with me or you can do it on your own. It is totally your call. But that would be tangent of 35 times 900, and this would be tangent of 35 times x. Okay. Now, again, the numbers are really atrocious here, but this is basically just an Algebra 1 equation. I'm going to go ahead and bring this x term over to the other side, so I'm going to subtract it on over. So I'm going to keep the 630, etc., right over here. And let's see if I have this. If I take this term and subtract that term, I end up getting 0.3722x. Okay, that looks great, which now is, we're one step away from solving for the variable. And if I do that, everybody, it looks like I get an x value of, and I'm going to go with about 1693.13, give or take. Okay, so I broke it on down, and then I solved for the remaining variable there. The question I guess I would have for you at this point is am I done? Have I answered the question? And if you look at the question, of course, and you don't have to underline anything, but it did say what is the height of the mountain. If you look at the way I described it, that's h. And I didn't solve for h just yet. As you can see, everybody, I solved for x. I know how far it is from that first observation to the base of the mountain there, but that's not what I was looking for. So I'm hoping you are in agreement with me that given x, we should probably substitute that in somewhere. I'm going to put it right there. There's so many different places to put it. But basically, if I put that in for x, I should be able to come up with h. So I guess I would ask you at this stage, can you take that 1693.13, put it back right in here, and multiply it by the tangent of 47 degrees, and that should give us our height. And if I remember correctly here, and I have something on my paper, I'm hoping it's exactly what you get, but I have about 1815.66, and I think we are in meters. And that looks pretty good. Again, just in terms of right triangle trig, you can see this is certainly harder than some of the ones we've seen before. And I think it's a little more realistic in nature. So from a surveying standpoint, taking one reading right here, taking a second reading right here, as long as it's on level ground, and we have this horizontal distance, you can see mathematically we can figure out that height. Okay, and a good problem. So take a look at that, please, and kind of go over the aspects of each step and make sure it makes sense to you. All right, on to the next. Let's go get example 2. And as a matter of fact, this is one that we have seen before. And I think I mentioned at the time that we would come back to this problem when we have a little bit more of a background. So if you remember correctly, just to refresh memories here, we talked about the linear speed of a point at the equator. And as the Earth revolves, I think we got something about 1,037 miles per hour. So as the Earth is rotating, somebody at the equator is moving 1,037 miles per hour, give or take. And I think the following question was, well, what about in Boulder? Do you think it would be faster or slower than somebody moving at the equator? And I think we all came up with the idea that it would be slower because it's a smaller distance. The circle at Boulder is smaller than the circle at the equator with the Earth revolving. So it's a smaller distance in the same amount of time. So to cover that smaller distance, we would be moving slower in Boulder than at the equator. Well, let's figure out that linear speed. So let's go for it right away here. Enough preamble. I'm going to try to draw this as big as possible on my board, and you guys do the same on yours. But basically, here's sort of the premise to rehash. Here's the equator right there. And then here's Boulder right up here, give or take, at the 40th degree mark. And so that's what I have at this point in time. And what we were looking for, I believe, if I remember the way I had set it up at the end there, is we need this piece right there. We need the radius of the circle that we revolve around at the 40 degree mark. So we need that piece. So some of the information that kind of went into that, of course, was using the concept of latitude. So what I did is kind of set up this piece right here. There's your 40 degrees by definition. So initial side going to the equator, terminal side going right to Boulder, and that is a 40 degree angle created. Now everyone, if you kind of remember the way I alluded to this, is we can draw sort of from center to center, basically a vertical line, and that would create a right triangle right in there. And so what we're going to have to do is find out this R using right triangle trigonometry. Now there's probably one more piece missing, maybe 1.5, give or take. And so let me fill that in for you. Radius of the Earth, and as you can see, radius of the Earth going to the equator, going to Boulder, etc. There's your 3961.3 miles. That's absolutely perfect. Now we can use a couple different angles here. Here's the other thing I was thinking of. This is 40 degrees, the latitude for Boulder, and I actually do want to use that particular number. So maybe some of you are kind of thinking, oh, if that's 40, then this is 50, and we can kind of run with the 50 and figure it out. I would actually encourage us to actually use the latitude itself here. So what I'm going to ask you to do, just using some basic geometry, if you remember the idea of alternate interior angles, if this is 40, everybody, then this acute angle is 40 right in there. And so here's what I guess I would ask. We know a couple things. I'm going to kind of start it out. But ultimately, I need a way for us to find that R value. And so I guess let's start out with this piece. We know it's 1 revolution in 24 hours. This is how we set up that problem before, and it just makes sense to kind of set it up the same way now. Revolutions to radians, everybody. And so again, a good little review for us. 1 revolution in 24 hours. I want to change revolutions to radians. So everyone on your paper, if you would, 2 pi radians is 1 revolution. Cancel, cancel, and that would be pi over 12 radians per hour. And everybody, that is W. Absolutely. And again, I think we've talked about this before, that is fixed for everyone on the surface of the Earth. So the angle for their radius as it revolves around is pi over 12 radians per hour. Okay. Now everybody, let's figure out how we're going to pull off this radius of our circle at the 40th degree mark. So the way I see it, everybody, is right triangle trig. Here's my 40 degrees that I'm going to focus in on. I need this side right here, which is the adjacent, and I have this side right here, which happens to be the hypotenuse. Need adjacent, have hypotenuse. Well, there's only one of the primaries that goes with it, and that's cosine. So the way I'm reading it, everybody, is that the cosine of 40 degrees is equal to our R value over the radius of the Earth, which was, just so happens, the hypotenuse of that triangle that I drew in. So see if that makes pretty good sense, because we're going to solve for R momentarily, but it looks like it is cosine ratio. Okay. Now, everyone, let's go ahead and cross multiply here. I'm hoping you're okay with me writing something like this, and I'm going to do this for a very particular reason, and I'm going to ask you to do the same. That is r, everybody. That is the radius of our circle. 3961.3 times the cosine of 40. Okay. Well, if you actually solve for that, I have it on my paper here. It looks like the radius of our circle is 3034.53 in miles, of course. So miles times that constant right here stays in miles. So everyone, think back to circular motion if you would. V equals RW, and we have R, and we have W, and so it's a matter of just now putting that in play. So you can see what a great problem this is. In fact, we're going to expand on this in just a few minutes. But basically, we needed that right triangle trig to come up with our radius. Now that we have it, everybody, I've got 0.53 miles times the pi over 12 radians per hour. Radians, again, is unitless, everybody, so it's essentially going to be in miles per hour. And then just let the calculator take over here and do exactly that piece. And if you multiply these together, that times the pi over 12, I believe you end up getting about 794.44 miles per hour. And that looks outstanding. There's some great math that goes into exactly what we did there. I want you to look that over and think about that for just a few minutes, because example 3 is going to expand on that. What I'm going to ask you to do is come up with a mathematical relationship for the linear speed for anybody on the surface of the Earth, depending on its latitude. So let's get into that piece. Alrighty, so example 3 is that culminating part here. And it says, write a function, represent an object's linear speed, so everyone, this is going to be our dependent variable here, as a function of its angle above or below the equator. Essentially, everybody, the latitude. So linear speed as a function of its latitude. And that's exactly what we're going to pull off. Now, I would encourage you, I don't have the board handy to kind of go back and forth, although I suppose I can do that. But you have your paper there. Look at what we did for example 2, and then think about how that's going to help us figure out example 3 here. Well, let's start it out, everyone. I think we all know this to be the case. V equals RW. Now, what we've already talked about, of course, is W is going to be pi over 12 radians per hour. That's not a big deal. So, as a matter of fact, just maybe even off to the side here, I'm going to do this. W equals pi over 12 radians per hour. That's constant for everybody. Now, here's what I need you to think about. How can I come up with the radius for anybody depending on the latitude? So, think about it for a moment, and then all you have to do is look back to the previous one. I will go back to my other board here, and you can see kind of why I wrote it. Well, for Boulder, which was at 40 degrees, and here it is right here, everyone, we used that cosine ratio and then just cross-multiplied. Isn't this right here how we got our R value? We took the radius of the Earth, 3961.3, and we multiplied it by the cosine of our latitude. And so that's it. That's how we get the radius for anybody's circle, as a matter of fact. The radius of the Earth times the cosine of the latitude. And so that's exactly what I'm going to put right here. So R equals 3961.3 cosine of the latitude. And we'll call that theta, by the way, momentarily. But now you can see it all come together. All I have to do is multiply those two pieces, and I've got my V. Okay, so let's see exactly how that's going to work here. I have this on my paper, and you can see if you agree just the way I wrote it. I've got my 3961.3. Pi is also a constant, so I'm going to attach that to the numerator as well there. So 3961.3 times pi times the cosine of our latitude. I'll call that our theta. That'll be our independent variable, everybody. And then notice just the divided by, and I had a 12 in the denominator. And so I'm going to divide it by 12. And that looks perfect. I think that is going to do it. There are a couple other ways to kind of look at this, by the way. If you want to ask about it, you're more than welcome to. But the other way to kind of perceive this particular problem is it's based on the Earth's circumference. And again, I could modify it, but I don't want to overwhelm and inundate you with too much information here. So I'm going to stick with this. This is probably the function in its most simplified form, 3961.3 pi times the cosine of theta, and then divide by the 12. Given any latitude, you can come up with the linear speed. And you'll do a couple of those, of course. Just make sure you're in degree mode on your calculator and you get a nice decimal degree for your theta. And you can apply it nicely. Okay, so 2 and 3 I think go beautifully together. If it doesn't click for you for whatever reason, please let me know. But I liked doing 2, in the one in Boulder, to kind of set up 3 here for anywhere on the surface of the Earth. Okay, well that should pretty much wrap up our right triangle trig. So now it is time, as I mentioned before, to really define the 6 trig functions beyond the other 2 representations. So this is going to be for the third and final time. So if you remember, we looked at 6 trig functions as represented on the unit circle. Then we looked at 6 trig functions represented using right triangles. And now what we want to do is represent the 6 trig functions for any angle at all in either units, either degrees or radians. And so again, this will be our last time kind of taking a look at those. And then what we're going to do is really explore the behavior of these as the angle changes, as the number changes, essentially. All right, well, let's give it a try. So here's what I'm going to ask you to do on your paper, if you don't mind. As big as you can get here. I'm going to sort of do a circle approach on this, and I'm going to show you a different way on the next notes worksheet. But for right now, give me a pretty big coordinate plane if you get an opportunity. And I'm going to ask you to do just kind of a small circle right in here. And I'm just going to think of this as my unit circle, if that's all right with you. So give me a little 1, 0 right there. And then what I'm going to ask us to do then is draw really a circle sort of on the outside. I think it just works better visually. Something like this, what would be called a concentric circle. Something along those lines right there. And what I'm going to do, of course, is now have my initial side in standard position, just like that, running across. And then I'm going to have my terminal side rotating off the initial side, exactly the way I've described it before from the very beginning, something like that. And now, everybody, I want a little theta right in there if we can. Now, I'm going to try to fit all this in. Even on my big board, it's not easy to do, but I'll see what I can accomplish. And then I'll ask us to get a little assistance on labeling some things. So here's what I'm going to ask you to do, everyone. And we've seen this diagram slightly before in a different context, but I'm going to ask you to drop the perpendicular and create a little right triangle right in there. And then for where this terminal side hits this circle, everyone, can you drop the perpendicular and give me a little right angle right in there, please? Each of those right triangles has 3 sides to it. I need us to label the 3 sides. And then what we're going to do is explore the relationship based on the fact that those 2 right triangles are what are called similar, meaning that their ratios are equivalent for all of the corresponding sides. So let's do the bigger one first. I think that'll be a little easier. And then the smaller one I'm going to see if I can write out as best as possible. So everyone, here's what I'm thinking. The horizontal side from here all the way to there. I'm going to have to put it down here, guys. That's x. Horizontal distance on the coordinate plane from the origin, that's x. Everybody, the vertical distance from here to here, that's y. Everyone throw a little y right in here. Now if you notice, this hypotenuse of the right triangle really represents the radius of the circle as that terminal side is moving around. We've talked about this before. If we were to track a point on the terminal side from here to here, it moves in a circular path. So that is the radius there, and then I have my x, I have my y, and I have my r. Okay, that's the 3 sides in the big triangle. Now, everybody, what we want to do is get the 3 sides in the unit circle triangle that I drew. Let me start with the easy one here. We all know that the radius is 1, and we kind of talked about that's what makes it so powerful. You can literally see those values unfold because the radius is 1. Now here's the interesting piece. I want the horizontal part and I want the vertical part. Well, we all know, everybody, that the horizontal part from here to here is the x-coordinate. I'm not denying that at all. but I actually now want to relate it a little bit to trig. And think about this for a second. How did we define x on the unit circle? Well, anytime I hear x, especially when thinking unit circle, it's the cosine of that angle. It's the cosine, in this case, of my theta right in there. X is the cosine of that angle in radian mode, or the number of units around the unit circle. And if x is cosine of theta, then everybody, we all know this piece right here. This is going to be the y value, but because it's on the unit circle, and I'm going to have to kind of draw this right in here, but because it's on the unit circle, the y is sine. And so what I have basically is three sides in this small right triangle in this unit circle: cosine of theta, sine of theta, and 1. Okay, now everyone, let's go ahead and start putting this together. Basically, what I want us to do is formulate some proportions. Because they are what are called similar right triangles, all of those ratios of the corresponding sides are equal. So watch how this plays out, everybody. So I'm going to go like this. I'm going to go two sides in the small one, and then two sides that correspond in the large one. Be with me on it, and then we'll start to put this together. So everyone, I'm going to relate this and this right here. And I'm going to do it off to the side before getting it completely. But basically, I would say the sine of theta over 1 should be the same as the ratio of the corresponding sides in the larger triangle. And so if I went here and here, then I hope you would all agree, everyone, that I'm going here and here. So sine of theta over 1 is really the same as y over r. And now, everyone, for the last time, we can define exactly what that sine ratio is equivalent to. For any angle, it's basically the vertical distance over the radius, what I'll call the direct distance. It's a ratio of those two values. And if you remember, on the unit circle, the radius was 1. That's why sine of theta was just equal to the y coordinate. That's just what made it nice and easy to see. But truly, this, everybody, is how sine is defined. And we'll look at all those values unfold in that regard. Okay, let's keep it going. So cosine of theta, I'm going to do this side to this side right here. So I'm going to do cosine of theta over 1. And everybody, let's match up the sides here. So it's horizontal over the radius. Well, let's do the same. Horizontal over the radius, everybody. So cosine of theta is now the ratio of x to r. So I'm going to come in right here. I think I have room. And that's your number 2. Again, we're going to really box these up. We have to know these completely as we are able to move forward. Okay, now this one's a little harder because I didn't necessarily talk about this piece. We're going to see this in sort of the next unit. But essentially, what I'm going to do is now relate these two sides, sine of theta to cosine of theta. And again, I'm not sure, maybe intuitively you knew this to be the case, but right now, if I match up those two sides, vertical and horizontal is y to x. And as it turns out, sine of theta over cosine of theta, for any number, as a matter of fact, is actually equal to tangent of theta. And so there's where you get your third primary ratio. Tangent of theta is y over x. Okay, good. So those are your primary three. Again, the secondaries we don't do a ton with, but we should know those as well, and we'll look at their behaviors too. But basically cosecant, my fault. Cosecant is r over y. Secant, everybody, r over x. And cotangent is x over y. So everyone, when you get an opportunity, really put a big box around those, and that represents as complete as it's going to get. And as it says, finally beyond the unit circle and beyond right triangles for any angle in either degrees or radians. And that's what we're going to start taking a look at. Okay, so any questions with that, please don't hesitate to ask. But you do need to know those 6 really well. Basically, it comes down to every angle has 6 ratios that goes with it. And those 6 ratios are based on 3 components, everybody. the horizontal distance, which is x, the vertical distance, which is y, and the direct distance, which is really r, the radius of the circle. Okay. I think we just need to fill in a couple more pieces, I guess, based on that premise. I'm going to skip this just momentarily, come right back to it. But basically, here's what we know. Every angle in existence has 6 ratios that goes with it. Okay, and those 6 are defined by sine, cosine, tangent, cosecant, secant, and cotangent. Now, not for every number will they be defined, but every angle has 6 ratios that goes with it. And the value of each of those ratios is based on 3 things, as I've alluded to already: x, y, and r. Okay, and that's how they're defined up above, and we're going to do, obviously, a variety of problems that kind of deal with this piece. Now, if you just take one more look there at the diagram, and I'll go back on the board, if you look at x, y, and r, could you formulate a little relationship amongst those 3 quantities? So here's x, here's y, and here's r. You're going to see a lot of problems where you're given 2 of them, and you're going to need to find the third. So let's set that up, a nice relationship amongst those 3. And I'm hoping you all see, because it's a right triangle, Pythagorean theorem is really going to apply here. So x squared plus y squared is equal to r squared. You'll probably see me represent it a little differently. It's the same thing, of course, but basically this. R is equal to the square root of x squared plus y squared. Okay. Good. Well, we'll stop right there for today and pick up this idea on the next notes worksheet. But there's just a few more good right triangle trig problems to take a look at. So please do that in the meantime. If any of the stuff on the back doesn't click with you right now, let me know, but maybe give it just another day, another notes worksheet to kind of put it together. Alrighty, of course, thanks for listening. If you have any questions, just let me know. And I appreciate all your help with this.